Okay, we're in 2.3 still, and now we're going to see how we can identify and use the properties of quadratic functions in their graphs to also apply the knowledge and solve applications of quadratic functions. So just to remind you, this is where we left off. Here's a generalization again of what we've learned about parabolas, the graphs of quadratic functions. We have the vertex. The vertex also helps us define the line of symmetry, this axis here, x equals to h. The vertex is either a maximum, as seen here, or a minimum. And the parabola opens up if a is bigger than 0, and opens down if a is less than 0. So one application here is to solve quadratic inequalities. Sometimes we might be interested in solving these quadratic inequalities in a way where the expressions themselves express revenue or profit. So we might want to see for what value of x the profit is bigger than or equal to 0, for example. So how do we solve a quadratic inequality? Really, the secret is to pretend it's a quadratic equation, solve it, then graph the parabola, see if it opens up or down, and go from there. Here's the process explained. The inequality holds for those values of x for which the graph of f of x is at or above the x-axis. We've graphed our inequality here on this graph using a graphing calculator, and then we're seeing where is this bigger than or equal to 0. Well, the part of the graph that's bigger than or equal to 0 is the part that I'm highlighting here. It's the part above the x-axis. This is where f of x is bigger than or equal to 0. Right? This is our f of x. Thus, we need the values of x, so the value here and the value here, for which this happens. Where does that happen on the x-axis? Well, using the intercept method on our calculator, we know that these values are negative 0.5414 and positive 5.5414. Let me illustrate this on my graphing calculator. Okay, so we have entered negative x squared plus 5x plus 3 into the y equals editor of our calculator. We're going to hit zoom and use zoom standard. Negative 10 to 10, 10 to 10 is the window. And here is our parabola. Now, we're trying to only find the part of the parabola that's above the x-axis, right? This part here. So, and I don't know if you guys could see the entire graph here, but let me see if I can move this around just a little bit. So there you go. You could see the graph on there. So in order to do this, we could use the second and intersect or zero feature to find the zeros. I'm going to demonstrate it for one of them, the one on the left, just so that you guys could see this on the viewing window here. Here we go. Let's do it. So I go to second, and then I do calc, which is really the trace key, and option 2 says 0. So select option 2. You could either scroll down to it with the arrow and hit enter, or you could just select option 2 on your number pad. Okay, well, using this option, I go ahead then and I select the left bound and the right bound. In other words, I go to the left of the 0 and I hit enter when I'm to the left of it, and I go to the right of the 0 and I hit enter again. And notice these two arrows and dashed lines appear. I have managed to put the 0 right between them. The calculator asked me to take a guess. I just hit enter, and it spits out the answer of negative 5.413,813. So that's how they got that first point. Negative 0.5414. That was the answer on our slides here. Okay, you repeat the same process for the right one, and that's when you have the interval for which f of x is bigger than or equal to 0. So that's how you deal with quadratic inequalities. Why don't we take a look at another application of quadratic functions, this word problem that we have here. So we have this peach orchard farmer who now has 20 trees per acre. It says each tree produces on the average 300 peaches. So one tree gives us 300 peaches. Okay, and he currently has 20 trees per acre. Okay, so it says for each additional tree that the farmer plants, the number of peaches per tree is reduced by 10. So for any additional tree that he includes, the number of peaches is going to be reduced per tree by 10 peaches. How many more trees should the farmer plant to achieve the maximum yield of peaches? What is the maximum yield? There is a lot going on in this problem, So with problems like this, with word problems like this, applications where there's a lot of relationships you have, the easiest thing to do is illustrate a few cases to see a pattern. Let's do that. So in case 1 here, the yield, actually in general, our yield is going to be the number of peaches per tree multiplied by the number of trees, right? The yield is how much peaches you get out of the entire farm. Okay, well, he currently has 300 peaches per tree, and we're told that he has 20 trees on his farm. That gives us 6,000 peaches total. Well, if he plants one more tree, then what happens? We were told that the number of peaches will be reduced by 10. So for the number of peaches per tree, we're now getting 300 minus 1 times 10, because he's planting one more tree. Okay, that's going to be multiplied by the number of trees. Well, since he's planting one more tree, then the number of trees is increased by 1. So really we have 290 multiplied by 21, that's 6,090 peaches. What if he plants 2 more trees? Well, planting 2 more trees means that he's going to lose 2 times 10 number of peaches per tree, or 20. And with that in mind, he still has to multiply by the new number of trees, which is now 22. Okay, so we have 300 minus 20, which is 280, multiplied by 22. He ends up with 6,160 peaches. So compare these numbers, and you're seeing that his yield is increasing. The total number of peaches is increasing here. So let's see if we can generalize this situation now that we've seen the pattern. Let x represent the number of additional trees that he plants. Then the yield is just going to be 300 minus 10 times x, the number of peaches per tree, multiplied by 20 plus x, the number of trees total. Okay, and you could FOIL this out to get this quadratic equation. Negative 10x squared plus 100x plus 6,000, right? We FOIL in order to see this. Well, to find the maximum yield, note that the y of x function is a quadratic function. And not only that, its graph, the parabola, is opening downward because a is negative. Hence, the vertex of the function will be the maximum value of the yield. We graph this using a graphing calculator. Here's the graph. The y value is in thousands, and we obtain that the vertex could be found also that way, right, with the calculator. We obtain its value that way. Or we could do it algebraically, completing the square, and both are down here for you on this slide. So anyways, the final answer here, I guess I should jump to, is 6250. So the farmer should plant 5 additional trees to obtain a yield of 6,250 peaches. Okay, and again, this is just the coordinates of the vertex. So we completed the square to find the vertex algebraically, or you could have just graphed the function into your y equals editor, right? The function that you had here. Negative 10x squared plus 100x plus 6,000. That was right here. Okay. And there it is. So 5 trees should be planted to give us a yield of 6,250 peaches. This is in fact the maximum of the quadratic function. Since the value of a is negative 10, so it opens downward, the vertex is the max. Let's take a look at one more example. This is another break-even analysis problem. It says the financial department of a company that produces digital cameras has the following revenue and cost functions for X million cameras as follows. So the revenue and the cost are given, and the domain we're told is between 1 and 15 for both. Well, remember, break-even points are the production's level at which revenue equals to cost. So if we want to find the break-even points algebraically to the nearest 1,000 cameras, all we have to do is set revenue equal to cost and solve for x. So we solve the two, we set the two equal to each other here, right? This is revenue, this is cost, and the solution is done on the slide for you using the quadratic formula. So we FOIL things out, we put all the x's together on one side, everything else on the other. Then we set one side equal to 0 actually to use the quadratic formula, and we obtain x equals 2.490 or 12.530. The company breaks even at those values for x in millions, okay, rounded to the nearest thousands. Finally, we could have also graphed the cost and revenue functions on a graphing utility, right, like our calculator, and looked for the intersection points. That's another way we could have obtained the answer, as shown before, how to do that on the calculator.